Again, the advent of code. Let's see what lies in store. Today, day 17. Now, light is in the air. We've got a malfunctioning experimental energy source. A set of cubes in a pocket dimension. Well, how can we resist? We've got an infinite three-dimensional grid. At every integer coordinate there is a cube, which is either active or inactive. They're almost all inactive except for a small flat region, which is our input. Some of them are active and some of them are not. The energy source boots up by executing 6 cycles. Each cube only ever considers its neighbors, which is any of the 26 other cubes it's adjacent. During a cycle, all the cubes simultaneously change. So we're doing 3-dimensional game of life today. Change their state. If a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active, otherwise it becomes inactive. If it's inactive, so those are your standard game of life rules, but in 3 dimensions. The engineers responsible for this thingy would like you to simulate the pocket dimension and determine what the configuration of cubes should be at the end of the 6 cycle boot process. For example, consider this state. Even though the pocket dimension is 3-dimensional, this initial state represents a small 2-dimensional slice of it. Simulating a few cycles from this initial state produces the following configurations, which are going to be a bit hard to visualize, shown layer by layer. Okay. Must be symmetric, right? Not like that one. It's the same as that one. That one should be the same as that one. Anyway. After the full boot process completes, there are 112 cubes left in the active state, starting with your initial configuration. Let's have a look at that. Simulate 6 cycles. How many cubes are left after 6 cycles? All right. Let's cheat again. Just copy it in. Our input is this. So there's our input. And we'll break that into lines, let's say. So we've got our input, which is this. Let's map it to, we'll use a map as our data structure here, even though it's not terribly efficient. It's okay. The initial state are exactly, well, it's exactly, we use 3-dimensional coordinates, so we'll go I, J, hey, no. So we've got our lines, right? We've got our input. We can zip 0 across that. So now each line is tagged with its, what would you call that? The J coordinate maybe, or I coordinate. And then within those, we'll give them their J coordinates. Oops, didn't like that. What have I done? Oh yeah, whoops. Let's do it correctly. Maybe we'll get the right answer. There we go. So now what we should have there, maybe that's not what we want. Maybe if we go draw a line from the lines and draw a character from each line. Oops. Zip 0. And we'll call, and then if we go here, do they call them IJ? They call them more like XYZs. Maybe that's a better idea. Yeah, we'll call them X, Y, and Z to match their terminology. So we'll call each line, they all have the same Y coordinates. So Y, X, and then in this case, we'll just say that Z is Z is 0, right, for all of our input data. So pure X, Y, Z, C. Oops, didn't like that either. Oh, whoops, not lines. Input. So initial is a list of coordinates with their value, and there you are, right? So there's our initial state. And then it's just a matter of turning that list into a map. All right. So, oops. So our initial state is exactly one of these maps. Okay. Now to walk through the cycle, I need to think about this a bit, because it's not enough to walk through the ones that are in the map. We need to talk to their neighbors as well. Okay, so maybe let's figure out how we're going to compute the neighbors. The neighbors of a cell, X, Y, Z, are right, X prime is 0. Yeah, we'll do it like this. You draw an X prime, you draw a Y prime, and you draw a Z prime. And your neighbors are X plus X prime, Y plus Y prime, Z plus Z prime, but only if they're not all 0. So either X prime is not 0, or Y prime is not 0, Z prime is not 0. Okay, and that should, yes, fair enough. And that should give us the neighbors of 2, 2, 2. First of all, there should be 26 of them, yep. And they should look like that. Looks right to me. So now the values to consider, the values for which we need to recompute the state, are all of the neighbors of all of the active nodes. So in fact, we don't need to keep a map from yes to no. We just need to keep a set of the ones that are active. Maybe let's do that. So instead of map, let's have S. And here, you just need to go guard C is hash. Hash was active, right? Yep. And then instead of doing that, we just need that. So just the coordinates. Now it's sad. Okay, so now the type of initial should be just a set of coordinates. Yep. And we have the neighbors. And then all we need to do, so we need to recompute them all. So we need, like the set of things that we need to consider are exactly the set of our current active cells and all their neighbors. So what will we call such a set? The possible set. The possible set of S is S. In fact, is there a function in here? Yeah, unions. That's good. So I want the unions of all of the neighbors of all of the, so the unions of all neighbors of coordinate C such that C is in our set. So all the neighbors of all the active cells union together. And we'll throw in S as well. We'll throw in S. There we go. Oop. What's wrong with that? Why are you mad? Why are you mad at me? I expected a set and you gave me a list. Oh yes, fair enough. Yep. I did. Guilty as charged. So initial is just this set. The possible from initial is this. These are all the ones we need to think about. It's quite a lot. This is a bit scary. I'm not worried about part 1. I'm very worried about part 2. And then we need to compute. We just need to filter these. Okay, we can just filter these. So next, step S equals S from, so the computer list will say for each C in possible S. Oops. So for each coordinate, let's get the current state. So it's active if it's a member of S. S.member CS. And then it's simply if active, we need to get the neighbors. So let's get the activity states of the neighbors. So neighboring states is map. Just look, is that in S? For all of neighbors of C. And then N, let that be the number of these that are active. Hang on, I think we should just call that in. Because this is just all trues and falses, right? So it's just length filter it. Right, so that should tell me how many of the neighboring states are true. And then we just say if active, what are the rules again? If it's active and 2 or 3, or if it's inactive and exactly 3. So if active, then N equals 2, or N equals 3, or N equals 3. So it's actually a nice, you can simplify this a bit. If it's active and N is 2, or just if N is 3 in general, that's the new state. So it's just guard. So the new set of active things is all of these that meet this condition that either it's currently active and N is 2, or N is simply 3. That's it, I think. And then we'll see. So if we go initial, we go step initial, and then again, then we do that 6 times, we're good. So part 1 should just be, well, if we're really super lazy, we just call step 6 times. Why not embrace it? 1, 2, 3, 4, 5, 6, initial. It's not too bad. And it's just the, what do you call it? The cardinality of that set, s.size, is that what it is? Yep. 382. That's right. What's next? Oh God, it's 4 dimensions. Okay, it didn't quite work because we forgot a dimension. Not sure how we forgot a whole dimension. So same thing again by the look of it. Pretty much the same rules, extended to 4 dimensions, the initial state. We still get a flat bit. For example, So there's no, like, this visualization is just not going to work. Okay, starting with our initial configuration, simulate 6 cycles. How many cubes after the 6th cycle? This doesn't seem like a hard change from what we've got. So our initial state is xy now 0, 0. And we have to throw in a w. These all become xyzw. throw in a W. W is not 0. W. So let's just check the neighbors of 4. Didn't like that. 80. Just checking with the nub, make sure I haven't thrown in any duplicates accidentally. Never mind these beeping. And I think we're done. Is that everything? That was it. Everything else works just as well in... All the rules are the same, right? 2 and 3 and... Same rules, yeah. I think we're done. Now it still says part 1, but... Now, efficiency may be a problem. It's not going to be that bad, is it? We can be patient. Oh, there we go. 2552. Hooray! Well, that was fun. It was nice that part 1 and part 2 were so similar. I guess we got a bit lucky there. Thank you for watching.